Well, hello one and all, and welcome to our short on recursion. Now, how many ways are there for me to arrange this set of 3 cards? Let's look at it mathematically first. You could imagine that I have 3 places to put down each of these cards. I can put 1 card in each slot. Well, if I think about how many possible cards I could put in this first slot, it turns out I have 3 possible cards. I could put down any card in my set of 3. But once I put down that 1 card, once that spot is locked in, if you will, I now only have 2 possibilities for the next card. So there are only 2 possible cards I could put in this second spot. And then in this third spot, once I've put down the 2 other cards, I'm only left with 1. There's only 1 possibility for this last card here. So in terms of the sheer number of possibilities or permutations of this set of 3 cards, I could arrange them in 3 times 2 times 1 or 6 different ways. Now if you think about an entire deck of cards, which has 52 cards, the same mathematics applies. For that first card that I could place down, there are 52 possibilities in a regular deck of cards. In the next card, though, there are 51 possibilities, and 50, then 49, then 48, and so on, all the way down to 1. And if you do this math, there are, in fact, 8 times 10 to the 67th power possibilities for arranging a deck of cards. In fact, when you shuffle a deck of cards, you are likely putting it in an order it has never been in the history of the universe. So this kind of mathematics has a name, and maybe you've seen this notation before. This reads n factorial, where n is any number. Could be 52 for 52 cards, could be 3 for 3 cards. A factorial is a way of computing how many permutations or ways of arranging unique objects there are. So if we look at the definition of a factorial, let's look at some patterns we might see. We saw here that 3 factorial was 3 times 2 times 1, or 6 possible ways of arranging 3 different objects. Well, 2 factorial is just 2 times 1. There are 2 possible ways of arranging 2 different objects. And 1 factorial here is, just by definition, 1. We know there's only 1 possible way to arrange 1 object. Now, if you look hard at this, you might notice a bit of a pattern. Certainly, we can define a factorial as the number itself times 1 less than that, times 2 less than that, times 3 less than that, and so on, all the way down to 1. But there's probably a more simple way to define what a factorial really is. In fact, if I arrange these numbers a bit more like this, you might see the pattern more clearly. 2 factorial is 2 times 1, but 1 is 1 factorial. So we could actually say that 2 factorial is 2 times 1 factorial. And once we've done this, well, it seems to me like 3 factorial is actually just 3 times 2 factorial. We're defining what a factorial is in terms of another factorial. This is what we call a recursive definition, using the solution to the problem in itself. So let's take a look here at the general form of a factorial. In fact, if we go back to using n, standing for any number, turns out that n factorial can be defined as n times the factorial of 1 less than that number. And this is a recursive definition. We're defining the solution to the problem in terms of a slightly smaller problem, but still one that is a solution to this problem as well. So let's see how we could write this in code and take advantage of this recursive definition of a factorial. Well, I'll come back here to a program I've written called factorial.py. And in this program, I have here a function called factorial. It takes in an argument that I'll call n, and I've given here the value 3. So I'm trying to find the factorial of 3. Well, we said before that we can define a factorial in terms of itself. So I'll go over here to line 2, and I'll say this function should return n times factorial n minus 1. I'm going to try to solve this problem by actually using the solution itself in a smaller form in this case. But let's take a look at what 3 would do here. 3, we'll call factorial once, n will be 3. We'll return 3 times the factorial of 2. Okay, so we'll call factorial again. In this case, n would be 2, and we'd call factorial where n is now 1. We'd keep going, though, where n would be 1. We'd then say a factorial of 0, and then we'd go again and call factorial. N would be 0, and then factorial n of -1. And I think we've gone a little bit too far. So when you're defining these recursive solutions to problems, it turns out there are not just these recursive calls, but you also need what's called a base case, a scenario where you know the answer off the bat. And for factorials, we do know this. In fact, for a factorial where I give n is equal to 1, well, I know the answer to that. If n is equal to 1, well, I know I can just return 1. No more calls to factorial are needed here. So now, in my recursive solution here, I have both what's called a base case, a scenario I know the exact answer to immediately, and I also have my recursive call where I'm trying to solve this problem by using the solution but giving it a smaller version of the problem. So let's actually visualize what's happening in code when I call a recursive function. I told you, verbally before that we're going through multiple calls to factorial, but it can be helpful to visualize exactly what those look like and how we get from all those calls to our final solution. So what I'll do here is I'll actually debug this program, which will show us the values for its variables and the number of times we call this factorial function. I'll set here a breakpoint, a place our program will stop, where we can then step through it ourselves and see visually what's happening. So I will go ahead and I will debug this program here. And you'll see on the left-hand side that I'll get access to a few windows that are helpful for me as I walk through this program. One, you'll see down below, is the call. As I walk inside, I'll debug this program here. And you'll see on the left-hand side that I'll get access to a few windows that are helpful for me as I walk through this program. One, you'll see down below, is the call stack. This is the place where all of our function calls are going to go. When I call a function, I'm going to see it placed on top of the call stack. And when that function finishes being called, it will be taken off the top of the call stack. I can also see in this variables window the values of my variables within each call. So let's see what that looks like here. Here I am on line 8, and I'm trying to compute the result of this factorial function. Well, I want to see how this factorial function is running recursively. So I'll do what's called stepping into this function here. I'll say, I want to understand how this function is arriving at its solution. So here, we've now stepped into this first call to factorial. Notice you can see it here on the call stack up above our initial call to just the entire program itself. So here I am at the top of this factorial call, where n I actually see is equal to 3. So n is not equal to 1. This condition will not go into line 3 here and return 1. We'll instead go to our recursive call here, where I'll take 3 times the factorial of n minus 1, or 2. So let's step into this call to factorial and see what's happening here. In this case, we'll see n is equal to 2. And we'll see this new call to factorial placed on top of our call stack, just as we said would happen. Well, here, n is not equal to 1. We will not go to line 3. We'll actually up a burst arriving at its solution. On recursive function, well, I want to see how this factorial function is running recursively. So I'll do what's called stepping into this function here. I'll say, I want to understand how this function is arriving at its solution. So here, we've now stepped into this first call to factorial. Notice you can see it here on the call stack up above our initial call to just the entire program itself. So here I am at the top of this factorial call, where n I actually see is equal to 3. So n is not equal to 1. This condition will not go into line 3 here and return 1. We'll instead go to our recursive call here, where I'll take 3 times the factorial of n minus 1, or 2. So let's step into this call to factorial and see what's happening here. In this case, we'll see n is equal to 2. And we'll see this new call to factorial placed on top of our call stack, just as we said would happen. Well, here, n is not equal to 1. We will not go to line 3. We'll instead go to line 5, where we'll find, again, a recursive call. We'll take 2 times factorial of 2 minus 1, or just 1. Let's step in again, and we'll see this call to factorial placed on top of our call stack. But this one, we can actually quickly resolve. N is equal to 1, so this conditional will be true. N is equal to 1, we will in fact return 1. So let's see what happens. When I return 1 from this call to factorial, notice that it goes off the top of the call stack. We've resolved that call to factorial. And now that we've done that, we can actually resolve this call very easily. We now know the result of factorial of 1. It's in fact equal to 1, so we'll just return here 2 times 1. We'll go ahead and do that. We'll resolve that call. Now we're at our initial call, where we resolved factorial of 2. We can then return 3 times 2, and we're left with, at the end, a total of 6. In this case, this factorial function, given 3, has returned to us 6. So these recursive solutions to problems are a great way to build up solutions that take in some input, a smaller version of it, and then find you the answer, passing that solution back until you find the solution to your larger problem. This then was our short on recursion, and we'll see you next time.
This isn't shopping.
This video is a data extraction and web scraping tutorial for beginners. Now, I'm going to assume that you know a little bit of Python, but we're going to keep it as simple as possible. And I'm going to use some of the most popular and my favorite Python tools as we go along. Now, web scraping in itself is quite a large subject, but we're going to just scratch the surface a little bit, try and keep it as simple as we can. And we're going to code together a web scraper for a website. So when you look at a lot of basic examples, people sort of send you over to this website to have a look and to practice on. And that is all very well and good. However, I tend to prefer slightly more real websites because, you know, there's a little bit more to it for a project. So this is what we're going to be doing in this video. This is an online store. This is quite a common task for people that are doing web scraping. We are going to be pulling some information from this page for these products. Now, I mentioned at the top of the video that we're going to be doing an HTML scrape, which basically means that when we are asking the server, the website, for the data, we are going to be expecting to get HTML back. Now, obviously, this isn't going to work with a lot of modern websites, which are JavaScript front end. That's going to be out of scope for this video. If you want to know whether you can do this technique on any website, the best thing that you can do is just start by looking at the website, understanding how it feels, and then coming in to inspect element. And I'm just going to make this a little bit bigger. What we're going to do is we're going to use this little tool here to click on some of the information, something maybe like this price, for example. And you'll see down here that I have this element selected, and it's
Excuse me, sir, how old were you when you made your first million?
What is this for?
We're trying to get advice for the younger generation.
called this really long and obscure class, and then this data-UI type of sale-price. Now what I like to do is copy that information and then come over to the source of the web page, so view source, and then we're going to search in here for that. Now you can see that I have found it in this source. Now this is a good indication, not necessarily a given, but this is a good indication of the way that we're going to attempt to scrape this data that it's going to work. You'll also see that I have 13 of 21 matches, which means it's found an element called this 21 times, which is good for us. Okay, so we're going to come back to the website in a minute. We're going to start building up our code. Now, I am going to be using NeoVim to write my code, but you can of course use VS Code. That's absolutely fine. Any code editor you like will work. But whatever you do, I really strongly advise that you use a Python virtual environment to install your dependencies, because otherwise you're going to clog up your main system and you'll have so many dependency conflicts and errors. So I'm going to start with python-m venv venv. Now, if you haven't done this before, it might tell you that you need to install it, and that's fine. You can do that, just follow the instructions. Now, I'm on a Linux machine, so mine is venv. So I'm your main environment. To really strongly advise that you use a Python virtual environment. To install your dependencies, because otherwise you're going to clog up your main system and you'll have so many dependency conflicts and errors. So I'm going to start with python-m venv venv. Now, if you haven't done this before, it might tell you that you need to install it, and that's fine. You can do that, just follow the instructions. Now, I'm on a Linux machine, so mine is source venv, which is the directory we just created, bin and activate, and this is going to activate my virtual environment, as you can see over here. Now you'll notice that I called my virtual environment the same name as the actual module that I created it with. You can call it whatever you like. I just find this easier and simpler. So from here, what we can do is we can use pip to install the things that we're going to need to actually make this program work. So I'm going to do pip3 install, and I'm going to use HTTPX. Now, a lot of people say use requests, and requests is good, and there's nothing wrong with it. If you want to use it, you can. I think HTTPX is just a slightly more modern version, and also has asynchronous capabilities for way down the line if you ever get there. So we're going to install this. This will zip through and get that done. And then we're also going to do pip3 install selectolax. Now, again, selectolax is a much more modern HTML parser than something like Beautiful Soup. It's backed by the C modest library, which means it's super quick at parsing. It's my preference. I use it all the time. The downside, of course, is that this is CSS selectors only. I'm okay with that, but if you like to use XPath or whatever, or something else, you can use Beautiful Soup. The principles of this are going to be the same, but for this example, we're going to use HTTPX and selectolax. Now I'm going to create a file. I'm going to call it main.py. I'm going to open it in my code editor here. The first thing we're going to think about is what we need to import in. So I'm going to import in HTTPX, which is what we've installed, and also selectolax. So I'm going to do from selectolax.parsers. As you can see, the common use any element called this 21, but your workflow haven't done the instruction, or it might tell you that the dependency conflicts and errors. So I'm going to start with python-m venv venv. Now, if you haven't done this before, it might tell you that you need to install it, and that's fine. You can do that. Just follow the instructions. Now, I'm on a Linux machine, so mine is source venv, which is the directory we just created, bin and activate, and this is going to activate my
I'll be back tomorrow. I might, what am I thinking? I don't know anything on these virtual environments. I might do a quick thing on Visual Studio, just learn how to actually use it. Kind of new with all this. I really don't understand it. My file management's just atrocious. So, done with the class. I might just go figure that out tomorrow and double back.